The first idea would be to treat prompt engineering like training any machine learning model. So this is quite interesting. But we should always remember to include explicit success criteria and some input-output examples in the prompt. This is not always the best choice, but I'm going to tell you about a different approach. It might be a good way. Today, I'm going to talk a little bit about automated prompt optimization techniques and explain why we can treat prompt as a new hyperparameter. So I'm Julia. I'm working as a machine learning engineer at DeepSense, and my main area of expertise are NLP and LLMs. So today we're going to talk about manual versus automatic prompt engineering. I'm going to discuss the pros and cons of both approaches and compare them. Then we're going to move to prompt optimization techniques and see different popular ideas from recent papers. And as a final section, we're going to move to practical prompt optimization. And I will talk about different mistakes and failures that can occur during prompt optimization. I will also explain why DSPy might not be the best approach for your use case, and also demonstrate how cursor can be helpful while doing automatic prompt optimization. So, moving on to the pros and cons of prompt engineering, of different kinds of prompt engineering. So, when we're doing this manually, the main pros are that it allows nuance control and incorporates the domain knowledge of a human expert. So, if someone has some domain expertise, it's easy to incorporate it in the prompt, and also the human expert can control the shape and content of a prompt. Also, the manually shaped prompt is more interpretable and explainable because it's written by humans, so this is quite obvious. And also, it doesn't require any additional pipelines, tools, or infrastructure because we just do it by hand. But it also has some drawbacks. First one is that it's time consuming and it's hard to scale because it's just one person doing the prompt engineering. It also can incorporate the human bias, and also it's really dependent on human prompting skills. So if someone is a poor prompt engineer, also the generated prompts will be of low quality. It's also difficult to explore the space of prompts thoroughly because we come up with some ideas, but we might not figure out that there are some different prompt formats that might be more effective in our use case. And it's also harder to reproduce and version the experiments because we just doing it manually. So there's no versioning incorporated in this. So when it comes to automatic prompt engineering, the main pros are that it's easy to scale to different tasks in the dataset because it's just running, for example, in the cloud or on a computer, so it's easy to scale it. It can find some non-obvious prompt structures that can be missed by a human prompt engineer. And it's also optimized directly for a given metric. So, we know what we're aiming for and how well our prompt performs. But it also has some cons. The first one is that it requires additional infrastructure where we can run the prompt optimization process. Also, the discovered prompts might be harder to interpret or explain because they are generated, for example, by some different LLM or optimized in some automatic way. Prompts can overfit the dataset or the metric because we can just see the numbers that occur from the metric on this dataset. So we cannot be certain that it will always work as we expect. And because we do this iteratively, it might result in high API costs. So it's worth to monitor them. So this part is going to be about some popular prompt optimization techniques from recent papers, and I will present three different approaches that can be can be used to do this automatic process. So first approach is about using LLMs as human level prompt engineers. So it consists of three main steps. The first one is the blue box, where we can tell the LLM that these are the input and output pairs that we expect. So this is our data set. And we wanted to generate a prompt that could fit to this data set, could produce this data set, so to speak. And when we have different prompts generated by an LLM, we can run the evaluation. So we take our data set, we test the prompts using these data sets, and we measure some final metrics. So, for example, if it's classification, we can say it's accuracy, for example. Or we can use some LLM as a scoring model. It depends heavily on our task. And when we have a generated prompt, we take the highest scoring candidates, and we can also do some resampling. So tell the LLM, here's the prompt, and for example, rephrase it. And while we have final rephrased prompts, we can also evaluate them and take the best performing candidate as our final prompt. So this is approach one. The approach two is about edit-based instruction search. So basically, we start with some initial prompts and we apply edits iteratively. So for example, edits can be deleting part of a prompt, swapping some parts of a prompt, paraphrasing. So these are the yellow boxes here. So we have an initial prompt, we do some different edits to the prompt. Then we score the candidate prompts on our test dataset. And we can do this multiple times iteratively, treating the best prompt from each iteration as the base prompt for the next iteration. And after some iterations, for example, when our score doesn't improve, we can take the best performing candidate as our final prompt from the experiment. So it's approach two. And the third approach is the most flexible one because it consists of a meta prompt that tells the model the task description. So what it's going to do. So in this case, optimize a prompt. So we're telling the LLM how we think the prompt optimization process should perform. And also we have the solution score pairs. So in general, these are example prompts and example scores that these prompts could get. So this is our initial context. Then we pass it to an LLM that we treat as an optimizer. The LLM generates a pool of solutions, and we can use an evaluator. So it can be an LLM, but it can also be some metric like accuracy, precision recall, or whatever we put here. And we can get the scores and put them in the meta prompt for the next iteration. And we can loop over a few times until we're content with the solutions and return the top scoring solutions. So this is the most interesting approach because it's like optimization in natural language. So we're used to doing optimization in math. So for example, some gradient descent or some similar algorithms. But in this case, the LLM is doing something similar, but using natural language for this. So this is quite interesting, and it can be used for different optimization tasks, not only optimizing prompts, but also optimizing code, optimizing some different structures, not only prompts. So to summarize these three approaches, we have the first one, which was using LLM as a prompt engineer. So basically generating different prompt variations by an LLM. In this case, usually one iteration is enough, and the authors of a paper obtained similar or better performance than manual prompt optimization on some benchmark tasks that were about word and sentence manipulation. The second approach was about applying iterative edits to a prompt. So these were the edits with swapping, deleting, and so on. And it was better for task-specific prompts instead of the generic ones. But the drawback is that this approach can produce prompts that don't sound very natural because of these different edits that might create some awkward sentence structures. And the third approach was using LLM as a general optimizer. And this approach outperforms manually optimized prompts on different benchmarks. And the interesting case here is that LLMs can be used as a general optimization framework, not only for prompts but for different kinds of optimization, like optimization in natural language instead of optimization in math. So different view of this of the optimization process. So we finished with the theory, and now we're going to move to some practical tips about automatic prompt optimization and some ideas that can be used in our day-to-day work. So the first idea would be to treat prompt engineering like training any machine learning model. So this is quite interesting. And when we optimize something, we would like to make sure that it performs as well as possible. So the main things that can go wrong are when we're doing the manual prompt optimization without desired criteria. So you're basically just doing something, changing, and we don't know how it's going to perform. If it's better, if it's worse. So the problems are definitely subjectivity and inconsistency, because different people optimize. Some people optimize for style, some for example, correctness. So it's not mm, it's not the same. It's not the same way. So we don't know how it's going to perform. We also have no measurable improvement because there are no explicit criteria or metrics, so we cannot tell if this change helped us or it helped us in this case but made some other case worse. And it can do some local overfitting because we can have just a few examples then we look at, and it may fail on some unseen inputs that we didn't come up with. The second problem that might occur is prompt optimization without a data set, and it might result in selection bias. So we're optimizing only for those few nice cases that we've created, but there are also some edge cases that we just miss. So it's the second point, that we have no coverage guarantee and we can miss edge cases. And also there's the regression blindness issue. So the changes that break previously working behavior can go unnoticed because we don't have a data set. So we see that, okay, we fixed something, but we don't know that something else got broken. So it's hard to track it. And also there's the problem when we don't do prompt versioning and our experiments are not reproducible. In this case, we cannot recreate past outputs, so it's hard to tell if it's better or worse. Also, there's a problem with debugging because failures cannot be traced to some specific prompt. We just know that something got worse, but we don't know when. And we cannot do any rollback, so we have no guaranteed way to come back to a safe state. So, when it comes to common failures in prompt engineering and fixes for those failures, mm, so the first one would be trying to accomplish too many tasks in a single prompt. And the idea to fix it would be to split one big task into multiple smaller ones that are usually easier for the LLM to tackle. The second problem is when prompts lack specific details, constraints, or examples. So we should always remember to include explicit success criteria and some input-output examples in the prompt to guide the LLM and tell it what exactly is what we want. The third one is prompts that overfit to a single example. So we should always remember to have quite a diverse evaluation set and include some possible edge cases to be able to tell uh, whether our prompt truly performs well and is quite robust. The fourth problem is that prompts may be too large and contain some conflicting instructions. So we could think about creating some token budgets for a prompt so that it can contain the maximal amount of tokens or do some pruning. So when we have the generated prompt, we can try to figure out which parts can be removed from this and keep the performance the same. And also there's an issue of output quality degradation when we're working with different model version. And it often happens that the provider changes the version and suddenly our prompt starts breaking. So we should do the cross-model testing and also make sure that our prompt is minimal. So we're not leveraging some specific features of different model versions. In recent times, the very popular approach was using a DSPy. It's quite a famous framework for some prompt optimization, but it might not be the best choice for each use case. And I'm going to explain a few drawbacks of this framework. So the first one is that DSPy's programming model might be quite complex to understand because the abstractions are quite complex, and I think it requires some time to get used to it and to understand. So it's definitely not easy to start using it. Also, your use case needs to fit into the SPY's abstraction, so you need to make sure that what you're doing can be expressed in the language of the SPY. It also has a large import overhead and heavy dependencies. So when you import it, when you import DSPy, it just pulls a lot of heavy things and clutters your environment. Also, you need clearly defined metrics if you want to do prompt optimization with DSPy. So it's not always the case in uh, every time. And also, DSPy is still evolving, so there are many bug fix issues on GitHub that are not resolved. So it might turn out to be unstable in some cases. And also, it has some performance issues, so the prompt optimization time and resource usage can be quite large. So this is not always the best choice, but I'm going to tell you about a different approach. Might be a good way, a good starting point if you want to optimize your prompt. So we can use coding tools like Cursor, which is not quite obvious on the first look, but it might be very useful and a very good solution for some, for example, quick prototyping or quick prompt optimization experiments. So how to do it? We need to have our initial prompt that we've crafted manually and our desired metric. So let's say we have a classification task. So we treat accuracy as our metrics. We have some prompt for classification tasks. We have some data set with inputs and outputs, expected outputs, and we run the evaluation. So we take our LLM, we run the evaluation process, we calculate the accuracy, and we log all inputs, outputs, and scores to a file that will be used later. We need to create a file with instructions for Cursor on how to optimize a prompt. So what we expect from a good prompt, how it should tackle this task. That can be stored in the repository. And we add this file to Cursor's context. So the Cursor's context should contain this file with instructions, file with initial prompt, and file with the evaluation logs from the step one. And this is when we can ask the Cursor, hey, Cursor, optimize this prompt for me and take into account this data set, these metrics, and treat this initial prompt as a base one for you and try to come up with some improvements. And after we have the optimized prompt, we can create a pull request and set this evaluation step and the CI/CD pipeline. So we can program in GitHub Actions. And we can make sure then on each push to the prompt file, we will have this evaluation running and we can see automatically how the new prompt version performs. So to make sure that it works as expected, I've run a small experiment. So I've used the GPT-4o mini model and the dark humor detection dataset, which was about detecting whether it's a joke or it's not a joke. It's from Big Bench dataset. I've created the prompt for cursor with instructions on how to do the prompt optimization. So I told it what are its inputs, about its goals, rules, output format, and so on. So basically, instructions about performing the optimization process. And the results were quite good because my initial prompt was a very small one, and it had accuracy of 0.7. But after the optimization process, we can see that the prompt is much more detailed and much more verbose, and the accuracy is around 0.85. So it's quite a big improvement. So we can see that it might be very useful to use coding tools as prompt optimizers. So when it comes to conclusions, I would say that optimizing prompts using coding tools, for example, Cursor, could be the simplest approach to try first. And as we've seen in the experiments, it can bring significant improvements without much human work. The second conclusion would be that DSPy might not always be the best choice for your use case because it's quite abstract and quite difficult to learn and not not an optimal approach. It's also crucial to have training and validation data sets, also the metrics that you want to that we want to monitor, and also to set up prompt versioning to make sure that we can roll back to some better prompt or make sure which prompt performed the best. Also, as a tip, we can use a stronger model as the optimizer than the model that the prompt is meant for, and it usually yields better results because the stronger model is better as a meta optimizer than the smaller one. And also, there's a problem that optimizing a prompt can generate high API costs, so it's good to monitor the costs while running prompt optimization experiments. So, as a final conclusion, would be that you should treat optimizing a prompt as optimizing any machine learning model. So, if you don't remember anything else from this presentation, this is the final line that summarize everything. Thank you. So that's all for today. Found this useful, feel free to like the video and subscribe for more. And if you have questions or thoughts, please leave a comment below. And thanks for watching and see you next time.